Good evening, everyone. So, welcome to the second week live interaction session for the course Mechanical Operations. So, let's just wait for 1 or 2 minutes for others to join before we begin our session for today.
Okay, sir.
So, let's begin our session. So, let me just share my screen. I hope my screen is visible and I'm audible. So, let's start our session for today. So, good evening, everyone. Welcome to the week 2 live interaction session for the course Mechanical Operations. This course is offered by Professor Shabina Khanam ma'am from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL Swayam program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati. I conduct live interaction session for this course for the July to November 2026 semesters. So in the last live interaction session, we just let me rectify this. This should be week 2. Yes. So in the last live interaction session, we basically went through the introduction to mechanical operations. So we saw why mechanical operations is important, how it is relevant in different fields of application. We talked about how mechanical operations is related to particle technology as well as powder technology, and how it is going to be useful for chemical engineers. Further from there, we actually moved on towards understanding particle size and shape. So if you remember, we talked about the measurement of particle size. We talked about the different physical variables that were a part of this. So we talked about, in case of size, we talked about multiple different definitions of ferrets diameter. I hope you were able to recollect all those things. And then we talked about convexity, circularity, elongation. Then with respect to the shape, we discussed again on, we touched upon the concept of circularity, and then we defined multiple different kinds of diameters based on surface area, volume, surface area to volume ratio, based on their sedimentation rates and etc. Further, in the last session, we discussed about the particle size distribution analysis. We also saw the significance of why we need to do the particle size distribution. Major reason being is that the solid particles that we handle in our everyday life comes in variety of different shapes and size. So analyzing them, so since they come in multiple shapes and size, you actually go for a particle size distribution analysis. So we ended our discussion over there in the last live interaction session. So basically in the last live interaction session, our discussion ended on understanding how particle shape and size influences the application and the operation as well as processing. So today we will start our discussion from there. So as I gave an example even in the last live interaction session, so the particle size influences the property of the material as well as on the processing of the material as well. So for example, when you have a particle in a micro scale, their optical or electrical or magnetic properties will be completely different from the same material in the nanoscale form. So suppose if we take a material which has a material in a micro scale or in a microscopic form, and then you try to break it down using some top down approaches and then get it into nano scale forms, the properties that the material exhibited in the micro scale and the properties that the material exhibits now in the nanoscale will be completely different from each other. So that's how this particle size actually influences the processing about how the material gets processed as well as on the application perspective of the materials. So today we will discuss on fine grain size distribution. So previously in the last live interaction session, we were mainly focusing on coarse grain distribution, size distribution analysis. So over there we used the sieve analysis as a technique. So major problem that comes with the particles is, in case if the size of the particle is under 40 micrometers, then you cannot actually do sieve analysis. So under 40 micrometer particles, which are almost the which are like the fine grain size particles, cannot be analyzed using the sieve analysis. So in order to do the particle size distribution analysis for them, we basically move on towards some of the complex techniques that are available with us. So since sieve analysis is not possible, here for fine grain size analysis, we basically go for two different methods. So one method is called as Rosen-Ramler method and another one is Gates-Gaudin-Schumann method. So both these techniques are basically used for fine grain size distribution analysis, where the solids are basically in the powder form with their particle size in the order of magnitude lower than 40 micrometers. So these samples, since they cannot be analyzed using this sieve analysis, we go for these two techniques. In case of this Rosen-Ramler method, it is basically used for analyzing, or it's basically used to represent particles, or it is basically used for doing PSD analysis for powders of various sizes and shapes. However, there is a downside for this Rosen-Ramler technique. The major problem being is that it is mathematically complicated. So the mathematics that goes behind the size distribution analysis on how do you uh, use the particle size, on how do you represent this particle size distribution is quite complex. So for this reason, this technique is often not being used because it is computationally expensive. Mathematically very expensive. So it basically requires a lot of computation. So since it's computationally expensive, we basically do not go for Rosen-Ramler method. The next method that comes out that is most commonly used is the Gates-Gaudin-Schumann method. So that is probably one of the techniques that we will learn today, or that has been taught in the course content as well for week 2's live interaction session. So the Gates-Gauden-Schumann or the GSS model is typically represented as, just a second, GGS model. So the typical representation goes as x is equal to a times d average whole power b. Now here x is nothing but it is the mass fraction, sorry, small x is the mass fraction. A is going to be your size modulus. B is the distribution modulus, and D average is nothing but average particle size, or you can say average particle diameter. So this is how you represent mass fraction in terms of the average particle diameter. So here, does anyone know what is the physical significance of the terms A and B? They both are going to be a constant. A and B are constant. So this is a two parameter model. So A and B are constant. A is known as size modulus and B is called distribution modulus. But question is, what is the physical significance of the value A and B? So X and D average we know. One basically represents for the mass fraction and another represent for the average particle diameter. So we know what is the exact meaning of that. But what does it represent, or what does the size modulus and distribution modulus actually signify? Anyone? What is the significance of A and B? So B is something called distribution modulus that typically represent how broad the distribution is going to be, the particle size distribution. Whether that particle size distribution is going to be a narrow one, which typically means that majority of the particles is going to be in the same size range, or it does it represent the fact, or is it going to be broad, that is many particle that is you have larger number of particles with the different sizes, so that particular width of the distribution is usually gauged by the parameter B, distribution modulus. Now what is A, size modulus? How do you physically signify the parameter A, or what is the physical significance of the parameter A? So everything what we are discussing, as I repeated even in the last live interaction session, these are there in the course content as well. So kindly have a look at that, look at the course content. So what we are discussing here is mainly like a kind of a quick recap of what happened throughout the five lectures over the week. So size modulus basically represent how coarse the size distribution is going to be. Oh, sorry. How coarse the size distribution is. So this is the significance of A and B. So how coarse in the sense whether the entire distribution is going to be of a part of fine grain size particles, or does it going to have some coarser material or particles present in them. So this is the significance of A and B. How broad is the size distribution and how coarse is the size distribution. So this GGS model is typically represented graphically using a log-log plot. So you convert this equation into log form and then plot it. So if you convert this equation 1, let me represent this as equation 1. If you convert this into log form, then what you obtain is, or you can rewrite this equation 1 as log x equals to log A plus B log D average. So now you have a log. Now the entire equation is in terms of logarithm. So you can plot a log plot. Once you get a log plot, you can actually find that for a fine grain size particles, you will get a straight line. So in the log plot for GGS model, the fine grain size particles will be represented by a straight line. Again, this log plot will be nothing but the log plot between, let me just write this. The graph is going to be between mass fraction, that's nothing but it's a x, and the average particle size. So in this log plot, you will see a straight line. So that straight line basically represents for the fine grain size particle. Suppose if there arises a case wherein you are not able to see a straight line, then in that case, there could be a problem related to this data acquisition or the way you have performed the experiment. So for the GGS model, the log plot need to have a straight line, so that particular straight line, so that you can actually find out the values of A and B. That straight line represents for the fine grain size distribution. So based on that, if you see, B will be nothing but x by d average, or B is nothing but the slope of the log plot. And since you know the value of A, D average and B, you can calculate the value of A. So kindly, so you take a log plot. So on y axis you have log x axis you have log D average. So you plot it. So you will see a straight line. That particular straight line, if you take the slope, you will get the value of B. So that's what it represents. So y, this equation is something very similar to y equal to mx plus c. So if you compare this, y is your log x is going to be a log d average, m is going to be the slope. So if you compare the equation, the value of m and b are, the value of m is going to be b and c is going to be log a. So once you know the value of b, you can get the, or you can calculate the value of log a. Now, so this is about the GGS model. So this is particularly for the fine grain size analysis. So in case wherein you have particles wherein whose size is going to be less than 40 micrometers, and in those cases sieve analysis is going to fail. So this is for the discussion related to the fine grain size distribution. Now from here we shift our focus to effectiveness of the screen. So what do you typically understand when I say the word effectiveness of a screen? So screen is basically the sieve analysis part, which you use it to separate the particles into their respective sizes. So when I say effectiveness of a screen, what comes to your mind? Gives anyone effectiveness of a screen? So effectiveness of the screen typically means how well the particles are going to be separated, or basically you can say the efficiency with which a screen can separate the particles into their respective sizes. That is what you call it as effectiveness. Separating efficiency of the screen. To say in a very simpler word or a very straightforward way, efficiency of a or effectiveness of a screen is basically defined as a effective sorry effectiveness of a screen is basically represents the efficiency with which the screen separates the particles. So separating efficiency of a screen is known as effectiveness of a screen. Now this efficiency of the separation, and there is another one term which is the capacity. So here we will discuss about two terms. One is effectiveness, which is nothing but, as I said, efficiency of the screen. Separating efficiency of the screen. Now there is another one term that we need to discuss, which is the capacity. So what is capacity? Capacity is nothing but it is basically the amount of material that you feed to the screen. Mass of the material that is fed to the screen per unit time, per unit area of the screen. So basically how much material you are basically capacity is nothing but it's basically the amount of material that you are adding to the screen per unit time, per unit area. And effectiveness is nothing but the chance of those particles passing through the screen. To pass through the opening of the opening of the screen. So suppose if you are going to put very less material onto the screen, then the chances that the particles will basically pass through the size pass through, that the particles of the desired size will pass through the openings in the screen will be great or will be more. Suppose what happens is if you are going to put lots of material onto the screen at a time, then there may be chances that these particles will not pass through or will not be able or will not get a chance to pass through the screen. The major reason being is that when you add a large amount of material, there are chances that this material may stick together due to cohesive forces or due to some presence of moisture, and when they stick together they form a larger size, and because of which that particular material which got stuck together, that size and then the size of the screen does not match, and they remain on top of the screen without passing through. So they basically tend to clog the screens. So because of which their effectiveness basically reduces. So once you keep increasing the capacity, the effectiveness of the material is going to decrease. Again, it's not going to completely decrease. Initially as you keep increasing the flow rate or the capacity of the material that you are going to feed to the screen, the effectiveness will increase first. Then after a particular threshold, if you keep feeding the screen with the more material, the effectiveness will decrease. So major reason being is that the amount of or the chance that you provide to the material to pass through the screen decreases when you increase the capacity of the material that is fed to the screen. So it's basically kind of a inversely proportional relationship. So they are totally or highly dependent on each other. So keep this in mind, because these two parameters, that is capacity and effectiveness, are basically an industrial performance factor. So they determine, uh, they both are industrial factors which basically affect the application or the handling of the solid material in the industry. So now there is again another one thing that we need to look at when we talk about the chance, the effectiveness. So there may be chances that, so as I said, the particles need to be smaller than the size of the openings in the screen so that they can pass through. But again, this comes with a condition. So there are chances that since the particles that we are going to handle in real life are not going to be regular particles, or they do not have any regular shape, or like triangle or circle or square, since they are going to have irregular shape, so there may be chances that the particles may not pass through, even though the size of the particles is less than the openings in the screen. There may be chances that if the direction or the orientation or basically the configuration of the particle is not right, then these particles may not pass through the openings of the screen, and they may remain on top, and they may cause clogging. So this becomes very important aspect. So when we do this seed analysis, we need to what you can say, we need to repeat the analysis for 3 to 4 times, and also we need to move these screens or provide some sort of motion to the screens so that the particles can get, so that you provide a chance for the particle to change its direction or configuration so that it can actually pass through the opening. So sometimes because of this direction, there may be a chances that for these irregular particles, they may not be able to pass through the openings. So even in those cases, the effectiveness of the screen is going to decrease. Hence, for reproducible results, you need to repeat these analysis, the PSG analysis or the screen analysis, for 3 to 4 times, and you need to provide a certain type of motion to these screens so that you provide more chance for the particles to pass through the screen. Otherwise the result is going to be irregular, once because sometimes what happens is the particle exactly fits in a particular direction that it may pass through, whereas in case of a second scenario you may encounter with a condition wherein the particles are of the same size but they are not able to pass through the openings of the screen because they were in other orientation. So due to this there may be errors while doing the particle size distribution analysis, and hence this needs to be kept in mind that we are dealing with irregular particles. In case of regular particles, the scenario is completely different because there they will be equal from all the shape. I mean, their shape will be equal, their length will be is going to be equal, and from every direction if you are going to look at the particle they are going to remain same. So over there direction or configuration of the material is not going to be important, whereas in our case of irregular particles, direction and orientation is an important factor that we need to keep in mind while calculating the effectiveness of a screen. So this effectiveness basically depends upon how well it separates all the particles of the desired shape and how little particles of the size other than the desired size is going to remain present in the screen. So I hope you are able to understand. So effectiveness basically depends on two factors. One is recovery and another one is rejection. Effectiveness depends on two factors. One is recovery and another one is rejection. So by recovery what I mean is how well the screen separates the particles into their desired size. Whereas in rejection, it is basically about how little amount of material or little amount of particles of sizes other than the desired size is going to remain present. So this is rejection. So efficiency is nothing but, or effectiveness is nothing but, oh sorry, it is recovery times rejection. So you need to take into account both these factors. First, whether your material is able to separate the particles into their desired sizes that you want, and second thing is if it separates, how much amount of particles of sizes other than the desired size is going to remain present in that particular level. So these two factors basically affect the effectiveness of the screen. So there is a way to derive this. So the entire derivation or the mathematics is basically is there in the course. So here I'm just going to write the final you can say formula or the mathematical expression for the effectiveness. So kindly look through the course content for the full mathematics behind this particular expression that I am going to write it here, or that I am going to mention here. So it is yb by ya. Let me just wait for a few minutes. I'll write it completely because otherwise there won't be much clarity. YB by YA YC, just a second, YA. Times 1 minus. So this is the final expression for the effectiveness of the screen. So here YA is nothing but the mass fraction of the feed. YB is the mass fraction of the product, and YC is nothing but it is the mass fraction of the reject. So reject is nothing but how much amount of the particles is basically are present other than the desired shape and size. So this is how you define the effectiveness of the screen. And based on the screens, we basically go for the different types of, there are basically different types of industrial screening equipment. So that list is basically mentioned here. So when I say screening, there are different types of screens that are available. So in case of the industrial perspective, when you see the industrial screening equipment are as follows. So first one is gristles. So the basis, so first one is gristles, vibrating screens, gyratory screens, trommel screens, and banana screens. So the major basis of classification for this kind of screen is the size of the particles. So whether the particle is going to be a coarse particle or a fine particle or intermediate particle is what is going to determine what kind of screen can be used for the particle size distribution. So you can easily see here that if you have particle size within the range of 20 to 300 millimeters, you basically go for grizzles. Whereas in case of 480 mesh to 4 mesh, you go for vibrating screens. And similarly for gyratory, trommels and banana screens. So depending upon the particle size or particle size that you want to analyze, you basically go for different kind of the industrial screening equipment. So each type of the screens that you see is basically useful for certain applications. So it may not be like for different type of applications, you will have different types of screening equipments. So this is about the effectiveness of the screen, and in this again each and every screen there is a detailed explanation. So since our live interaction session is only for 2 hours, we won't be able to go through in detail for all of them. So kindly have a look at them in the course content. So you can look. So over there, every different type of screens are analyzed in detail. So please have a look at them. So, but the basic overview or the difference between each type of screens is this. They basically differ with in terms of efficiency, capacity, and their particle shapes. So, in case of grizzles, if you see, the capacity is going to be very, very high. However, in case of gyratory improvements, the capacity is going to be very, very low. So, depending upon the type of applications that we have in mind, different types of screens will be useful for us. So, any questions on effectiveness of screens or the screening equipments? Yes, anyone? So next we go for another concept or very simple one again, which is called as comminution method. Any idea on what is the term comminution means? Comminution. It's nothing but comminution means reduction in size, or you can also say size reduction. So basically, for particles, we basically do size reduction, and that particular concept is called comminution. Again, there are different kind of factors that basically affect this comminution process. There are several factors, in fact, which affects the size reduction process. But as such, when you talk about comminution method, it's basically it is nothing but it's the size reduction technology. So again, I'm not going to go in fact in detail about this. So kindly have a look at the course content. So any questions so far on what we have discussed? Anyone, anything? I have just given a basic overview on what was taught in all the five lectures, but since the last two lectures, we it's something more of like it's more like reading on own, so that's the reason I'm not putting more focus. So any questions? Anyone? So if you have no questions, then let me open this. So you can go through these questions and then be ready with the answer. So as usual, between the start of this problem session and then our concept. So as you remember, even in the last live interaction session, we splitted the session into two. One is concept overview and another one is the problem solving session. So let's just take a very quick break for for max 5 minutes. Meanwhile, these questions will be here, so you can have a look at them and then prepare your answers. So, or you can also take a break for 5 minutes. So, come back after 5 minutes. We will start our session by 6:05. So, where we will start solving the problems one by one. Again, this is just to make sure that people don't get exhausted in a 2 hour continuous session. Yeah. Okay, so let's begin the session. So let's move on to question one. The aperture size of a 70 mesh Indian standard screen. Again, remember this is the Indian standard screen. For American standard screens, the definition is going to be different. So, the aperture size of a 70 mesh Indian standard screen is 0.7 mm, 0.014 mm, 0.8 mm, 0.0133 mm. What could be the answer? Again, we defined what is mesh number for Indian standard screens in the last live interaction session. Anyone? So, what is mesh number as far as the ISS screen is concerned? Or ISS, sorry, Indian standard screens is concerned?
The number of opening for unit length, median length,
Yes. Did somebody speak up? I mean, it was not audible.
sir.
Hmm.
The number of opening for unit length, linear length.
That is fine, but that is what is a mesh number as such, that definition. But I am talking about, but I am asking, so with respect to the Indian standard screens, how will you define the mesh number?
Aperture size is expressed through the near decamicron.
So then in that case, what will be the answer for this question? So the mesh number is 70.
0.7. Mm,
zero point 0.7 mm. So answer is A. So basically the calculation goes something like this. So it says a deca of a micron, right? So okay, let me do it here itself. So a deca of a micron is 10 power 5 minus 5 meter. Correct, because micron is 10 power minus 6 meters and micron is 10 into 10 power minus 6, that is 10 power minus 5 meters. So if you convert this into mm, it is going to be 0.01 mm, and this is equal to one mesh. Like that, now our mesh number is going to be 70. So 70 times 0.01 is going to be nothing but 0.7 mm. So option A, the aperture size,
Okay, sir.
okay, of a 70 mesh ISS or Indian standard screen is 0.7 mm. So any questions related to this?
No, sir.
Okay. So let's move on towards the next question. The question is, which of the following screens is operated only horizontally? Gyratory screen, vibratory screen, grizzly screen, and none of the above. So we discussed. So we just went through few of the names of the screens, right? Gyratory, vibratory, grizzly, trommels, banana. So among this, which of the following is operated only horizontally? Is it gyratory screen, or is it vibratory screen, or is it grizzly screen, or is it none of the above?
Sir, none of the above.
Sure.
Sir, vibratory screen.
Okay. Anyone else? Any other answers?
No, sir.
Okay. It is gyratory screens. Option A. Kindly have a look at this, because this is a very this question is, you just need to look at this answer. So the screen that is operated horizontally is a gyratory screen, but again please check the course content once again, so that you were sure about the answer. So let's move on towards the next question. Which of the following process depends on particle size? Combustion efficiency of a coal, sponge iron production, settling of cements, all of the above.
All of the above.
All of the above, okay. Any other answers from anyone else?
All of the above.
All of the above. So all this process basically depends on the particle size. So if you are going to use let's say particles of bigger particles, then that will have a different effect compared to the particles of the smaller size. Suppose, let me put one more question. So suppose I take a bigger particle and suppose I take a smaller particles. Which one of of them will undergo combustion faster, or will undergo effective combustion compared to the other? So among the big particle and small particles, if I take two particles, which one will undergo combustion more effectively? Is it the bigger one or the smaller one?
Bigger one, sir.
Why? I mean, any particular reason?
Oh,
Any reason on, I mean, if it is, if there is a choice, then is there any particular reason for that choice? So try to identify the reason, because I'll put this as a question here. Just only two options. Is it small or is it large? And of course, you need to justify. I can give the answer. Probably, I think you can look for the explanation. So, the answer is smaller particles will undergo more effective combustion. But you need to tell me why smaller particles will undergo more effective combustion compared to a larger particle. There's an interesting concept behind that. So, kindly have a look at that, and then let us see this question in the next session. But then the answer is it's a small particle. So, kindly have a look at that. So, let's move to question 4. Particle size distribution cannot be computed through A. Comminution method, B. Gates-Gaudin-Schumann method, C. Rosen-Ramler method, and D. Sieve analysis. Particle size distribution cannot be computed through which of the following methods? Is it Rosen-Ramler, Gates-Gaudin, sieve analysis, or comminution method?
Combination method.
Comminution method, basically, because comminution actually means size reduction. You are going to break the
Size reduction.
particles to
Particles.
get a lesser size. So obviously that does not play any role in particle size distribution. However, in case of sieve analysis, it is basically you can do particle size distribution of you can do particle size distribution with the particles that have size greater than 40 micrometers. In case if it goes below 40 micrometers, or if you go for fine grain size particles, then you can either go for Rosen-Ramler or Gates-Gaudin-Schumann method. Again, one of the disadvantage with the Rosen-Ramler is basically it is mathematically more tedious. It is, if you say the computational effort that you are going to put is going to be more expensive. So that is the reason the most commonly used method is the Gates-Gaudin-Schumann method. So let's go towards the next question. This is about the Gates-Gaudin-Schumann or GGS method. So in GGS method, the straight line is obtained for coarse grain particles, fine grain particles, both A and B, and none of the above.
Both A and B.
Okay. Any other answers?
Fine particles.
So the Gates-Gaudin-Schumann method, if you see the log-log plot, it will be that particular plot will be both for fine grain as well as coarse grain particles. But then the particular straight line is only for fine grain particles. So for coarse grain particles, the curve will not be a straight line. It will be a curve linear. So that particular graph I will post it along with the presentation. So you can look at it there, or you can also look at it in the course slides. So the answer to this question in Gates Gordon Schumann method, the straight line is obtained for fine grain particles. Once you get the straight line, you find the slope A value, X and D average. So uh, that is I think I explained the method of getting A and B values. It's a 2-parameter model. So let's move on towards question 6. If particles are to be recovered from the feed, then the final product should be undersized, oversized, both A and B, and none of the above.
Undersize.
Undersized.
It's going to be undersized.
Under,
So undersize is the correct answer. So can you define what do you mean by oversize and undersize?
Undersize is small particle and oversize is large particle.
Large particle with respect to what? Like there should be a reference, no?
oversize is reject on screen.
Okay,
Reject
and
method on screen.
passes through the screen. So
Passes through the
undersize
underside.
is, so the
Passes
undersize.
through. Undersize is the passes on the screen.
So the material
Passes.
that passes through the screen. And oversize is the material that gets retained in the.
Reject.
Okay. So I think there is probably no doubts with respect to this question. So question 7. Wheat contains almost 20 percentage moisture. Which of the following size reduction will be suitable? Dry grinding, wet grinding, both A and B, and cutting is required.
Dry grinding.
Dry grinding. Anyone else? Any other answers?
Sorry. Sorry, sir. Wet grinding. Because of the 20% moisture.
Okay. Is it dry grinding or wet grinding?
Wet grinding, sir, because of moisture is more content, 20% moisture.
Okay. Stationary screens are mostly used for fine particles, porous particles, both A and B, and none of the above.
Fine particles, sir, that is a.
Sure.
Yes, sir.
I'm talking about stationary screens. Anyone? Any other answers? One answer came out to be as what do you say? Fine particles. Any other answer?
Sir, option B.
Option
B.
Chorus particles. So fine particles are basically what do you say? Moving screens are used for fine particles, whereas stationary screens are mostly used for chorus particles. So the answer is B. Now, moving to the last, I think that one single MCQ type questions. Effectiveness and capacity of the screen are dash. Instead of saying proportional, I'm going to make this how they both are related to each other, effectiveness and capacity. Whether are they going to be dependent, independent? If dependent, how dependent they are, how they are dependent of each other.
Effectiveness is the chance of the particles to pass through the opening of the screen.
Yes. And capacity?
And the capacity is the mass of the material that feed to the screen for a unit time and for a unit
So how
area
they are
of the.
related to each other?
They are related in recovery and rejection.
No, that is effectiveness is nothing but it is basically it deals with recovery and rejection. But I'm talking about capacity and effectiveness.
Inversely proportional.
It's not inversely proportional, like you cannot say that way. The major problem is because initially when you increase the capacity, the effectiveness will increase, and this will happen until a particular flow rate of feed you achieve. Once you exceed that, then the effectiveness will decrease. So you can say that there will be initial increase in the effectiveness, and then after that there is going to be a decrease. So both effectiveness and the capacity are highly dependent on each other. So that is what we wanted to emphasize here, and that's what we saw in the an hour back we discussed as well. So if you take effectiveness and capacity, they both are not directly, you can say they are inversely proportional, but they do maintain a relationship of increase decrease with respect to the effectiveness. Basically it increases first and then decreases as a function of capacity of the screen. So, and why, if you ask? Because initially when the capacity of the screen is low, many particles are able gets a chance to pass through the openings in the screen. But as you keep increasing the flow rate, more and more the capacity of the material increases or on the feed, there are chances that these particles may stick to each other. It might be probably due to some cohesive forces, aggregation, or it may be chances that they get stick to each other because of the moisture content present in them. So when they stick to each other, they form like kind of like, what do you say? They clog the screens and they do not pass through them, and that because of which the effectiveness actually reduces. So that is the relationship. So please take care of this particular concept. So at low capacity, effectiveness increases because many particles gets a chance to pass through the openings. At a as capacity increases or at higher capacity, clogging happens, due to which chance of passing through the screen becomes low. So the effectiveness reduces as a capacity of the screen or with the capacity of the screen. Any questions in this? Okay, then I think let's move towards next one. So this was the question that I gave in the last week. I asked people to solve it. So anyone has solved this question? If not, please take this question right now and try solving it. Or otherwise, we will solve it in a few minutes, but please give it a try once. So the particle size distribution of material A is given. So size range is given, -2818 plus 2399 is 0.3. Then you have 0.45 for some other size range, and the minus 0.25 for some other size range. We are asked to calculate the arithmetic mean diameter of the sample. So what does this negative and the positive sign here represents? What does negative and positive sign represent? So negative sign basically represents that the particles will be of size under than the one that is mentioned. You can say that the negative sign basically represent the size range, represent the upper limit of the size range, whereas the positive signs represents for the lower limit of the size range. So in this case, it would be something like the smallest particles, the size of the smallest particle is going to be 2399 micrometer, and the size of the largest particle is going to be 2818 micrometers. So all the particles whatever you are going to have, they will lie in this range 2399 to 2818 micrometers. Now, based on this, you need to solve the problem. Just a second. Oh, I was just checking whether the recording is going on properly or not. Any idea on how to start solving the problem? So, first, what we should do? Any leads for this problem? So first we should calculate the average diameter for the particular size range. So let's do this problem in a separate slide. So the first this thing will be 2399 plus 2818 by 2. So how much is that? Sorry. 2399 plus 2818 divided by 2. 2608.5. Then for the second one, it is 2399 plus 1676. Please solve with me. In case if you get any answers, do let me know. 2037.5 for the second one. And how did I get this? I just next is 1676 plus 1405. So 3081 divided by 2. 1540.5. I hope, I don't need to write this same thing. Just add the two ranges, the size limits, and then divide that by 2. You will get the average diameter. Again, this is for particular fractions. So in that particular size range, the average diameter we have calculated. We are now supposed to calculate what is the arithmetic average diameter throughout that sample. So now what to do? Can you define arithmetic diameter as summation of NIDI NIDI divided by summation of Ni? Ni is nothing but is the number of particles. Is it possible to write it this way? So now we need to know how to calculate the value of Ni. Can I write Ni as Mi, that is your mass fraction, divided by Di times, that is your average particle diameter whole cube? Can I write it this way? We need to calculate the number of particles Ni. So we basically take the mass fraction that we have and we divide that with the di cube. Again, this will be a proportional. We are taking out the proportionality constant and then we are writing it as equal to. So please keep that in mind. So if I do that, mi is 0.3 by di cube, that is 2608.5 micrometers, the whole cube. Let it be in micrometer cube itself. Similarly, this is for the first size range. And third size range will be by whole power 3. So I'm just taking their respective mass fraction and dividing that with their average diameter. So so any questions? Now I know Ni, I have Di. So can I not calculate the arithmetic diameter? So which will be nothing but 0.3 by 2608.5 whole square plus 0.45. I'm just going to copy paste. This entire expression for better, this whole thing divided by Ni, which is nothing but it's basically the summation of all the three. So that would be a plus, I'll copy this and then So this, if you calculate, you will get the arithmetic diameter. If you wonder how I made this square term, so if you see here, Ni is nothing but Mi divided by Di cube. So in the numerator you have Ni Di. So that is Mi by Di cube times Di. So that will be Mi Di square upon the summation of Ni1 plus Ni2 plus Ni3. So if you do that, you will basically get the arithmetic diameter of the particles. Any questions or anything that is not clear here? Anyone? Anything that is not clear here? So I'll write it here. Mi by Di the whole square. So if you do this calculation, you will be able to get the final answer. Can you just quickly solve this problem and let me know what is the final answer coming? Any answers? So find out the answer for this. Now, in case if you have any doubts, please let me know. Now, let's move on towards the next question. So, following is a particle size distribution of three cuts obtained from a double deck vibrating screen, 35 and 48 mesh. The mass ratio of oversize, intermediate, and undersize is 4 is to 5 is to 6. Calculate the effectiveness of the 35 mesh screen taking oversize as the desired product. How to solve? This is something that is related to this week. Mass ratio is given. How to go about it? So you know the feed ratio, so I think you can calculate the mass fraction. So mass fraction will be nothing but 4 by 15 for the oversize. For the intermediate, it's going to be 5 by 15. And for the undersize, it's going to be uh, 6 by 50. So, what are the values? 4 by 15, 0.266, 0.266. This will be 1 by 3, though, that is 0.33. And 6 by 15 is 2 by 3, sorry, 2 by 5. So, that is zero point 0.4. Now you know this. So, we are basically con- our focus is taking oversize as the desired product, so we need to calculate the effectiveness at the 35th mesh screen. So let me just copy paste the table. I'll just crop the question. So with this we need to basically see what will be the feed at uh, let's say how many columns we need. Let this be the table for the time being. So feed at 35 mesh. So we need to now, and since oversize is our what do you say? desired product, we need to do the calculation. I think it's not fitting properly. So this would be 0.0021 times 0.266, and similarly the next one will be uh, what would be the next one? Point uh, 0.075 times 0.266, then it would be 0.18178 times 0.266, and for the 35 it would be 0.392 times 0.266. Is that right? I mean, beyond this, will there be any values? Yes. So since we are basically interested only for the 35th mesh screen, I'm going to take only the value up to there. So YB, that is your product, is the oversized product is something that you are desiring. So YB will be nothing but uh, 0.0021 plus 0.0075 plus 0.178 plus how much? Uh, 0.392. So what would be the value? So 0.0021 plus 0.0075 plus 0.178 plus 0.392, 0.5796. Now YA is the addition of all this. This is for the feed. So I had calculated the value previously. So let me just check once. It is 0.0056, sorry, 3 zeros. So this is by nothing but it's the multiplication of these. So let me just show that for one by value alone. 0.005586, I'm writing it as 56 plus 0.002 plus 0.00, sorry, 0.5813 plus 0.1280 is nothing but 0.18876. Now you know why B and why A. So once you know YB and YA, you can calculate the effectiveness of the screen. YB is known, YA is known, so you can easily calculate the effectiveness of the screen using the formula. So Instead of calculating YC, that is the reject, you don't need to calculate YC. Here you basically represent them only in terms of YB and YA and B as well as A. So you know YA, YB, B by A is nothing but 0.266 by uh, just a second, sorry, so it will be B by A is nothing but 0.266, that value is correct. So you know this for B by A value, you know YB and YA, so you can easily calculate the effectiveness by plugging it into that equation. Any questions in this? So your effectiveness, that value, since I calculated this before, efficiency is coming around 0.705. This is the value. Efficiency, or you can say effectiveness, is 0.705. Any questions in this? Anything that is confusing? So first we calculate the feed in the 30, that mesh 35. Once you know that, you can calculate YA is nothing but the sum of the feed in each of these mesh. YB is nothing but the oversize, and that is your desired product. You calculate the sum of that. Once you know those values, you just add, and then you need to calculate YB, YA. B by A is already you know. So you just need to plug in that effectiveness equation, and you will get the value of the effectiveness on the screen. Any questions? Yes. Any questions, or shall we conclude the session for today? Oh, oh, the old. So if you have no questions, then let us conclude. Let me stop presenting. So in case if you have doubts, you can let me know, or otherwise we can conclude the session for today. Okay. So thank you all for joining today's live interaction session. I hope you find this live interaction session useful. So our next live interaction session will be on 8th of August, same 5 p.m. to 7 p.m. So I take this as an opportunity to thank Professor Shabina Khanam ma'am for providing me this opportunity to interact with you all on this Saturday afternoon. I thank the NPTEL team as well. So the video lectures as well as the presentations will be uploaded to the course page soon. So in the course page for mechanical operations July-November 2026, on the left hand side, you can see at the bottom corner problem solving session. So if you access that folder, you will be directed to a Excel sheet from where you can access both the video recording, which will be uploaded to a YouTube channel. So once you click on that link, you will be redirected to a YouTube video, so you can access the video contents there, as well as the presentation file folder will also be uploaded. So in case if you have any doubts, you are welcome to email me. My email ID will also be present along with the slides, or you can also drop your questions in the Q&A section. So I'll try to answer to them as soon as possible. So thank you all for joining today's session, and I hope you have a great week ahead. And thank you, and have a great week. Bye.
Thank you, sir.
Thank you.
Thank you. Thank you.
Thank you.